something like a fraction of the cost, 10% of the cost of Portland cement. We use a lot of it. Something like 75% of all concrete and transportation infrastructure contains fly ash, right? So if we get rid of all of our fly ash, what do we do? I don't have the answer, right? I'm just saying that that's kind of where the trends look to be going, right? So we might need to be nervous about that. All right, well, let's look at slag, granulated blast furnace slag. All right, this is another material that, where it's available, it's used a lot. So in Virginia, we don't really have a source of it. You can sometimes import it. I know in Illinois there are some sort of local places you could get it. Here's the problem: supply currently meets demand. All right, so we don't necessarily have that much extra slag lying around. The other problem are probably our future trends of blast furnace slag are going to be decreasing. All right, if we look in the U.S., well, the U.S. never really produced much pig iron to begin with, but the U.S. is starting to tend towards more electric arc furnaces to produce steel, which is mostly sort of scrap steel, recycling steel, and that seems to be a global trend. All right, so we seem to be recycling steel more than making raw steel from iron ore. That means our sources of blast furnace slag were going to decrease, right? So again, doesn't really look like a viable outlook in the future. All right, what about natural pozzolans? All right, well, we only produce something like 70 million tons of natural pozzolans worldwide, not enough to replace fly ash, okay? Biggest problem with natural pozzolans is they're highly localized, have highly variable reactivity. Is it a future trend to use more of it? Maybe, but it's going to have to be regional. All right, if we look in the continental US where I'm in Virginia right now, yeah, there's no source nearby, right? That means it's going to be probably expensive. It's probably just cheapest to use straight cement at that point. Other parts of the world would be economical. So what's the future? I don't know. Okay. If you look at the future, maybe geopolymers or alkali activated materials. Well, if you're looking at a fly ash or a slag-based alkali activated material, well, you're running into the same issue of supplies. All right, well, there's a lot of people who like metakaolin, and metakaolin seems like a good idea, right? So the U.S. has some of the highest quality kaolinite clays in the southeastern U.S. and Georgia. We have a huge supply of it, but we're not making very much of it. There's only about 3 million tons produced per year, right? As opposed to in fly ash right now, we're using something like 100 million tons, right? So supply is not quite meeting a demand yet. Then there's this idea of these calcined limestone cements. Those seem promising. I haven't researched them. I haven't looked into them. All I can say is what I've seen at conferences and things. So maybe that's where the trends are going. Um, so it's hard to say. Regardless, cement's not going anywhere. Okay, so even though cement is the third largest CO2 producer in the world, it's a big industry. All right, so the cement sales in the US alone is $10.7 billion, right? And the US is only the third largest cement producer in the world. The US only produces like 2%. Where are we on there? Something like 2% of the world's total cement, right? And that's a $10 million market. If we go to the global market, we're talking $680 billion. Going into the ready mix industry worldwide, it's over $1 trillion. So is cement too big to fail? I don't know. Probably, right? We need cement. We use a lot of cement. So the question is, how do we make it more sustainable, right? If the question is we're not going to have much fly ash or slag going forward, what do we do? So my perspective now is hey, let's look at these recycled aggregates. Okay. So now let's just assume that cement's not going anywhere. We're going to be stuck with 100% Portland cement binders moving forward, right? It's still going to be producing a lot of CO2, right? Maybe there'll be other advancements in CO2 sequestration or something, right? But maybe now we can at least recycle some materials, all right? Stop using so much raw materials, okay, because we're also looking at other parts of the country, don't necessarily have unlimited supplies of high quality natural aggregates, right? Virginia is fortunate. We're one of the top 10. I think Virginia is the third largest aggregate producer in the US or something. We produce a lot of high quality aggregates. If you go to other parts of the country, that's not the case, right? So now they have to pay a lot of money to import it, or maybe they just look to use locally available materials, right? That's another way now to reduce our costs, reduce our CO2 footprint. So first thing I want to talk about is reclaimed asphalt pavements. So this is near and dear to my heart. This is what I spent my master's and my PhD researching. Uh, the idea here is that we produce a lot of reclaimed asphalt pavement in the US, well, in the world, right? I mean, what are the numbers? Something like 90, I think something like 94% of all paved surfaces in the US are asphalt, right? So pretty large fraction. So we produce a lot of RAP per year. We reuse a lot of RAP, right? We do use a lot of RAP into new asphalt pavements, but we're limited to maybe something like 15 to 40% by aggregate content. And in addition, a lot of the asphalt pavements tend to favor using the fines, which have a higher asphalt binder content. So that leaves a lot of the coarse fraction behind. So what else can we do with that coarse fraction? Well, hey, let's toss it into concrete. Problem. We reduce our strength. Okay, we reduce our modulus. Some other properties don't necessarily seem to be affected too much, but if we're looking at, let's just say, pavement design, right, where a lot of pavement design is driven purely on strength, right? If you went to a contractor and said, hey, um, here you can use this aggregate, it's free, right? You now don't have to pay for the aggregate. Oh, but you're going to lose 20% of your compressive strength. Well, they're just going to laugh at you and tell you to go away, right? So the question is, why do we have this decrease, right? And if we can figure out why we have this decrease, can we then figure out how we can mitigate that decrease, right? And actually improve the properties, okay? So this isn't as simple of a problem as just adding silica fuel, okay? Right, so you can look at a lot of your SCMs. If you add some slag, add some silica fume, right? You typically will densify the ITZ, reduce some porosity, produce more CSH. That all sounds great, but we didn't see that effect with RAP and concrete. All right, and I'm not showing that data because we just don't quite have the time. So you just have to take my word on it, or look up some papers, right? So we were finding that no matter what we kind of did to the binder, right, you can probably reduce the water cement ratio a bit, but it didn't have that great of an effect. So clearly something was going on with the microstructure. All right. And so this is pretty much where my PhD work went, was trying to figure out why microstructurally is asphalt not playing nice with the cement binder. Okay. So if you look at a lot of the historical perspectives on that interfacial transition zone, right? So that's the zone around the aggregates that basically form due to packing inefficiencies. ITZ has a higher porosity. Okay, so now you have a larger volume of a lower modulus phase essentially in your bulk concrete. You have these larger calcium hydroxide crystals, all right, which some argued would allow for easier crack propagation. And then we have the actual, sort of chemical or physicochemical bond between the cement paste and the aggregate surface. Okay. So what I did was pretty much looking at one and two, or one and three, I should say, were really the focus of what I looked at in my PhD. So to study the ITZ, you first have to epoxy impregnate your sample. All right, you have to fill in that void space with epoxy so that you're stabilizing the microstructure, and then you have to polish it fairly flat. Okay, and then you're going to do scanning electron microscopy, specifically backscattered electron imaging, and then based on the grayscale, you can start to pull out different components of the microstructure. And then you can start to look at what's the distribution of these phases as a function of distance from the aggregate interface. Okay. Now, this in and of itself caused some problems because some of the epoxies that we would typically use actually acted as a solvent for the asphalt. So that meant we had some issues with epoxy impregnation, but we eventually were able to successfully epoxy impregnate the sample and develop some nice micrographs like this one. This was a 1-day sample. You can see there's quite a bit of porosity. But already just looking at this image, right? So you can kind of see where this asphalt mastic is, right? And you can already see very close to the interface, already just visually, it appears to have a fairly high porosity relative to the bulk. Okay, so skipping through all of the image analysis processing we went through, uh, I was eventually able to pretty much make these sorts of plots of porosity, unhydrated cement content, and calcium hydroxide as a function of distance from the aggregate interface or the wrap interface for the wrap samples. And looking at different samples, we can clearly see that there's a much higher porosity when we're looking at wrap. All right. And we seem to have quite a diminishment in the amount of calcium hydroxide. So that was already ponderous. So what's the cause for that? That's something I'm still looking into. We're running some experiments at Virginia Tech now to try and answer some of those questions. So I don't have all the answers, right? But at least empirically, this seems to give a pretty good indication why we are seeing a reduction in strength and modulus, right? So now already if we just have a larger, more porous ITZ, right? So now if you look at the total volume of your concrete, you have a larger proportion of that volume that's this larger, more porous ITZ, right? So that already was one thing reducing our modulus. And then we started looking at the actual sort of bonding energy between the asphalt and the cement. All right, and so here we're looking at the surface free energy using the sessile drop method. This was actually one of Alcadi's students was doing this work at the time, and so that's how we kind of got into this to see if we could apply it to this study as well. So there might be people at Illinois still doing this type of work. I don't know, but I mean, here's the camera that's at A-Trail. We basically had the sample of asphalt. You put these different drops on it. You measure the shape properties of that drop, and you're eventually able to then calculate these sort of free energies of adhesion. You can calculate energies of cohesion as well. Calculate some interfacial energy. Um, and again, I kind of had to skip over a lot of information here, but we found that we could change the interfacial energy between asphalt and cement paste by doing some oxidation to the asphalt. All right, so we were able to find that we could uh, make some modifications and actually increase the energy of adhesion. Okay, but the problem was we still had that larger, more porous ITZ. The other problem that's kind of fascinating is that the work of cohesion of the asphalt, all right, so the energy it takes to split the asphalt apart was still less than the amount of energy to split cement from asphalt. Okay, so the energy of adhesion was stronger than cohesion. So now this is telling us that great, you can do whatever you want to improve the bonding. It's not going to help you because the cracks are still going to propagate through the asphalt, right? And so this is really why we don't see any effect of for instance adding silica fume. All right, so even if you're adding silica fume, yeah, great, you're improving the bulk paste strength and durability. Yeah, but your cracks are still propagating through the asphalt. You haven't fixed that problem. All right. So what we're able to conclude is really the sources of problems with RAP were these two issues, right? That larger, more porous ITZ. And again, great. We found we could reduce the ITZ a little bit with silica fume. Not as good as if we did it with like a limestone or a granite aggregate, but we could improve it a bit. The problem was your cracks are still going to go through the asphalt film. Okay. So this right away should tell you that, hey, maybe we can't really think about concrete with recycled aggregates in the same way that we think of conventional concrete. All right. Are there any questions on wrap? 'Cause I'm going to kind of switch gears and then also talk a little bit about the microstructure of steel slags and recycled concrete. If not, we can talk at the end. Whatever. How are we on time? Okay. Do we have a question? I heard some noise. Maybe not.
Alex, I have a question.
Mhm.
Before you move so far from from my question.
Yeah.
So you calculate the porosity and on the portion based on the slice that you take the image on, right? That's the 2D slice.
It's a 2D slice, correct?
Yeah. So do you think that if you take a sample in 3D, the proportional in 2D is gonna be linearly proportional in 3D?
Yeah. So of course that's absolutely a fairly significant issue, right? And so the best people have been able to do is Paulo Montero a few years ago did a sort of ITZ study using I believe it was some sort of nano X-ray CT at the synchrotron, so you're able to get significantly better resolution, and was able to pull out the porosity, right? And so if you have this idea of a 3D ITZ, yeah, you can pull out kind of more information that way. The method I used with that 2D cross section is historically what's been done, right? We have a lot of data on it all the way going back to the 1980s when it was pioneered by Karen Scrivener. The idea is if you do collect enough images, right, you're hoping that if you collect enough images from enough different aggregates, you kind of get a average effect of that ITZ distribution. But yeah, absolutely, it's not a perfect method. So does that kind of answer the question? I know it's not a perfect answer.
Yeah, I don't know. It's like if you say the proportional of the porosity in 2D is like, let's say it's 20%. What do you estimate is gonna be in 3D?
Oh,
Because the 3D is the one that you really pull, right? When you compress something or you do the pull test, or you're gonna do in 3D. You're not gonna do in
yeah.
the zero thickness slice,
And
right?
yeah, the other thing you have to factor is the porosity in that ITZ does change as a function of orientation, right?
Right.
So you do have greater
Exactly.
porosity kind of on the bottom side of an aggregate versus the top side.
Exactly.
Yeah. So again, I mean, the best we could do with this type of research with the capability we had was looking at that 2D cross section. So
Yeah.
maybe that would
Okay.
be an interesting study to see the 3D characteristics of the ITZ. I'll have to see because that study by Paulo I'm thinking of, I think they just pretty much calculated like a total porosity. They didn't get into any sort of 3D, sort of volumetric ITZ characterization.
Mhm.
That could be pretty interesting.
Yeah.
Yeah, like maybe just taking sample at different thickness or something like that.
You're saying for 3D or for 2D?
It would be 2D, but like it would be layers of 2D instead of just one single 2D per sample.
Well, yeah. So you could eventually segment it from the 3D reconstruction. You could take slices from it.
Yeah.
Yeah, or you try to render an actual 3D volume of all
Yeah.
of those pores.
Thanks, Alex.
Yeah. No, that would be an interesting idea. I'll have to think about that now.
I'm doing that thing now. That's why I'm curious how it's
Oh,
gonna be in
so you
how
are
it's gonna
doing
be.
you're trying to do 3D porosity
I'm
or
doing it's like, for example, in my case is I do on right now. I'm doing a liver cell, right? Liver cell actually gonna be must be 3D. But what is the pathologies is they do is they just cut it, right? They cut it to get the 2D histology. So my job is from the 2D histologies, what can I interpret in the 3D? So So we have some assumption in order to reconstruct from 2D into 3D, right? But of course, it's one of the assumption is that it's going to be homogeneous and isotropic. But I don't know, because that we know that aggregate is not going to be isotropic, right?
Yeah.
So it's going to be different case by case from my study in your study. But it have the same concept about proportional in 2D and proportional in 3D. It's going to be somehow related. We can do the approximation, but we have to do based on assumption that we make.
Yeah. So what technique are you using to study the I guess the 3D shape of these cells?
So for example, there's a study in order to, because you also looking at the space distribution of aggregate, right? So we are doing the same. We transfer. We have the space distribution of let's say cell centers. Then we characterize how can we quantify the space distributions using some function. I call it it's the pair correlate function, if you heard about that. So pair correlate function in 2D and 3D, it has some relationship that you can transform from 2D to 3D. Of course, it's an approximation, but from my study, it kind of accurate. When I compare between the ground truth and estimation, I see it accurate. So it worked in my study, but I don't know how about yours?
Well, you probably have a simpler phase that you're
I don't know.
trying
I never try.
I mean, are you trying to scale up a multi-phase material, or I mean, you did mention it was isotropic, so is it really just one thing you're trying
We assume
to
isotropic,
scale?
but the way that you have you ever, there's a method they apply in stereology. Stereology, they study how to construct 3D from 2D.
Yeah, so I remember looking at that
so
years ago.
we apply. So there's a method. I don't know. I don't remember exact the name, but I think the Buddhists, they say that there's a relationship between the number density in 2D and the number density in 3D.
Okay.
It's based on basically it's based on the thickness that you assume and the maximum diameter that you can find in a 2D slice. So of course, when you cut the 2D slide and when you cut the 3D and you get the 2D, you will find, I assume that on the particle in the slide is going to be a circle, right? So if it is a circle, then I can find the maximum diameter in the histology 2D slice, right? So the chance that when I cut a sphere, cut it through the center of the sphere is the highest. When I cut 1,000 times through the sphere, most of the time I will cut to the center. So it's the most likely I will get the maximum diameter, right?
By taking the average, you're saying?
By taking the average, exactly. So I say, okay, I cut through the centers and I cut through I can find the maximum diameter. So I can find the maximum diameter in 3D if I assume that everything is model dispersed. Then from there I can find I can approximate how it's going to be in 3D from 2D.
But the other issue we're primarily running into here is if we go back to this image, your pores are not discrete and they're percolated. They're connected.
Right.
So how do you define the diameter?
That's why we have to assume it.
Yeah.
In my study, liver cell, we assume it's circle.
Okay.
Here is maybe you have to assume. Of course, this is like a polygon, but you can roughly draw a circle around it, right? Roughly,
yes, but again,
it's gonna be perfect.
The pores are not necessarily discrete. right? They're not necessarily separate or segmented. So where do you draw a boundary for one port of the next if they're connected?
That's what you had to tell me into detail about research.
That's yeah, maybe that's why we haven't seen this in ITC studies.
Yeah, maybe
That's
here's what I see.
yeah.
What I see that maybe not. Maybe you can count the porosity based on the. I mean that here we can see that aggregate, we see that the porosity, we see some other thing, but most of them is the aggregate and right. So I can take I take the aggregate and I do the. I take the and then subtract the proportion of aggregate. I can get something else. I don't know. Maybe it's just a concept. I don't have a.
It's an interesting idea. I have to think about this now. It's a good point. So
Yeah, right now
yeah.
right now like you used to talk about Mondo. She used the SEM, right, to find the 3D. It is the techniques because it when we shoot that one we get a spectrum, the spectrum of a frequency and the contribution of each frequency. So that it tell you about the spacing because the frequency and then spacing is just the inverse, right, proportional. So from there you know the spacing, and then from the spacing distribution you know how what is that called, how the particle related in the space relatively. So we still in the process of developing the techniques in similar to SEM using ultrasound. So I keep you updated if I have something new about that. Yeah, that's my question. Thanks, Alex.
Yeah, so keep me updated what you find, because then we'll see if we can apply it to these complicated microstructures. All right. Well, I don't want to keep everyone. Where are we on time? I don't want to keep everyone here. If and of course I'll keep talking until you tell me to stop talking. So two other areas I just want to talk about, and I'll try and just mention it fairly quickly, so we don't go too much time over. But two other critical recycled aggregates we can think about is something called steel furnace slag, and then another one, recycled concrete, we'll talk about as well. So steel furnace slag now is not the same as blast furnace slag, right? These are completely different. You get blast furnace slag from going from iron ore into the blast furnace to then produce pig iron. All right, so kind of a somewhat refined iron. And then from there you go to a steel furnace, so either a basic oxygen furnace or an electric arc furnace, to then now refine it further and start to make your actual steel product. All right, so steel furnace slag is now a byproduct from um, the electric arc furnace or the basic oxygen furnace. All right, so this is not cementitious. It actually can be quite expansive. It can contain a lot of free lime or free magnesia that expands when it's reacted with water. But otherwise, it's a very hard, durable aggregate. All right, and it's mostly been overlooked because there were a lot of big failures in the US back in the 80s. And so the US, everyone basically just said, forget it, we're not worrying about this stuff anymore. And for the most part in the US, it's not really being used. So what we had looked at a number of years ago was looking at a handful of different sources of slag. All right, so here are three different types of slag. We compared it to a control of dolomite, right? So virgin aggregate. And we pretty much found that there's a lot of variability, right? So depending on where the slag was coming from, you can either get an increase or a decrease in strength. In general, you seem to get an increase in modulus, probably because it's a higher modulus aggregate, right? So then once you compound that with the composite modulus of the system, right, you kind of increase the overall modulus. Problem is there's a lot of variability with this material. All right, sometimes it can be highly expansive, sometimes it can be non-expansive. Some people have shown that there can be reactive phases in the material. Other people found that it's entirely non-reactive. All right, so there's a lot of variability. And so some of the things we're working on now is trying to develop some sort of rapid sequence of tests to try to decide, all right, can we or can we not use this exact source in some sort of application? So when we looked at the microstructure, right? So we kind of did the strength study again and said, okay, why are we seeing these differences? When we looked at the microstructure, we found that the source that gave us the highest strength, this electric arc, this specific type of or specific source of electric arc slag, um, we sort of saw that this is fairly uniform microstructure um, with not a lot of variability necessarily. Compare that now to this, right? So now this is that slag that gave us the lowest strength. And what we found is that there was kind of this outer layer of high porosity, different composition. And if you look in the literature, people have found that composition to be calcite, sometimes calcium hydroxide. One study claimed it was a type of CSH. Other people say it's a calcium carboluminate phase. So somehow on the surface of this aggregate, we are getting this sort of bulk change in microstructure, right? So we almost have like the hard interior of the slag aggregate, and then we have this sort of ITZ, you can think of it, right? This sort of weak zone, and then it's going to bond to your cement paste, where there's going to be another ITZ, right? So that's really probably why we saw a lot of reductions in strength with this material, was because of that. And then this other slag type we looked at just had really variable composition. Some sections were very porous. Some sections had that same sort of, surface altered layer, whatever we want to call it. And other sections were very hard and condensed and fairly uniform. All right. So a lot of high variability here. And so when we then looked at the ITZ again, much like we did before, we did see some similar sort of porosity distribution issues. So that steel slag number 2, we found the ITZ actually behaved fairly similarly to our control, the dolomite, right? And that's the one that gave us the highest strength increase, right? Where as opposed to that BOF and that LMF, so slags 1 and 2, those both had some reductions in strength relative to that. And so we did find that there was a higher porosity there too, right? So that's another way we can now relate maybe why we've been seeing those reductions in strength. Okay. So really what we were able to conclude from steel slags is some of them are great, right? Some of them have excellent mechanical interlock, are fairly non-reactive, non-expansive, and they would probably perform exceptionally as an aggregate in concrete. But because there are these other sources that behave terribly, right? How do we actually, pick which one to use, right? Or if you're just going at it blind and say, hey, let's use it and let's not study how it's going to perform, well, now you have to think about how do we modify our design to account for that variability? Or do we, right? Or maybe we just say, we're not going to use any steel slag at all, right? That's carry on as we have for the past, 20, 30 years, just not use it. Okay, last one I want to talk about real quick is recycled concrete. Um, so recycled concrete's interesting because now you have a lot of variability in the composition. Okay, so you kind of have your old aggregates, your old mortar. You can have these old ITZs. If the material was undergoing some sort of durability issue, right now you can have some latent ASR. Maybe you have some high chloride contents, high sulfate contents. Localized microcracking. Maybe you got microcracking during the crushing operation. So again, there's a lot of variability with recycled concrete aggregates, right? And this is another reason you can talk to some people, right, in the industry that say, I'm not going anywhere near recycled concrete. It has way too much variability. We can't predict it, right? And is that the future we have to look forward to, right? Are we just going to carry on business as usual? I don't know. So yeah, here's kind of, we can see these old and new ITZs. So that was one of the challenges we see with RCA. So that's one thing, right? So now you can have this sort of weak plane in the old aggregate from the old ITZ, but then you can also have these weaknesses with the new ITZ. Biggest problem with RCA that I would argue is the absorption capacity. Okay, RCA will absorb a lot of water. Okay, we've looked at RCA fines that have moisture absorption anywhere from 6-7%. We looked at one even up to 12%. Okay, so if you don't account for that when you're mixing your concrete, you can run into a lot of issues, right? So if you don't measure the moisture content of your RCA and you don't account for this moisture difference and you mix your RCA dry into your concrete, guess what? That RCA is going to want to suck up all of the water that's supposed to be there for your cement hydration. That's going to cause a lot of issues. So that's what we were looking at in this study. Is we basically took a 0.42 water cement ratio cement paste, right? And we didn't change the moisture there. Okay, and then we took RCA that's saturated, oven dry, or like 80% SSD, and mixed that as is into the paste. Okay, so yes, I know that that's sacrilegious. We're not accounting for the moisture content there, but that's what we were trying to study. We're trying to figure out what happens if you mix an oven dry RCA that wants to absorb 7% moisture. What's going to do to your local water cement ratio? The answer is it's probably going to screw things up quite a bit. All right, so here again, we can look at our microstructural cross sections, right? And then if we look at these porosity distributions, we kind of saw some interesting behavior. Okay, so because the oven dry RCA probably absorbed a lot of moisture, right? It actually locally affected the water cement ratio. So you can see we actually got less porosity kind of in the bulk microstructure, right? Kind of the right side of that curve, right? So that would tell us that we're actually improving the sort of bulk microstructure. But look at the difference between the bulk and immediately near the aggregate interface. There's a pretty big porosity difference there, right? And that's going to cause problems. So if you do look at studies that have looked at these different moisture contents, we find, again, there's a lot of variability. Typically, your best strength and best durability concretes are when your RCA is at this sort of sub SSD condition. So kind of like 80% SSD. So it still absorbs some moisture from the microstructure, right? One idea is that it kind of sucks in also some cement paste, and so you get this sort of better, mechanical interlock. Whether or not that's happening, we don't entirely know for certain, but that's one of the going ideas in the literature. Okay, so we're at least able to show that yes, the aggregate moisture content, the RCA moisture content, seems to have an influence here, right? And so that's something that we should be concerned about. Okay. The other problem is if, let's say, your RCA is completely dry, right, and it wants to absorb, let's say, 9% moisture. If you mix that RCA dry into your concrete and then adjust your batch water, the problem is RCA doesn't absorb all that moisture that quickly. Okay, so studies have shown that it might take 24 to 48 hours for RCA to become fully saturated. So it's kind of a useless method then to try and just adjust your mixing water, because now you're just changing your local water cement ratio. You're actually going to be reducing your strength, right? So here again, we can't necessarily carry on with the same assumptions for conventional concrete as we do with RCA. And so now that's really where my conclusions are going. Okay, so if we use these recycled aggregates, right, can we use them? Should we use them? All right, the answer is yes and no, right? I'd like to tell you that yes, I have the perfect answer, and the answer is yes. But in reality, it's yes and no. Okay, yes, you can use it in concrete, right? There's nothing stopping you. right? There's no physical barrier just stopping you from using it. But you need to adjust your performance expectations, right? Concrete with recycled aggregates is not going to behave the same way as conventional concrete. First of all, as long as you know that and understand that, we might be able to come to a better consensus on how to use these. So again, you can't treat these materials the same. All right, the failure modes are different. Okay, the microstructural behavior is different, right? We talked about how cracks in concrete with wrap, cracks are still going to propagate through asphalt cohesion, right? It's going to propagate through the asphalt film. That's not something we really have to worry about with, let's say, a limestone aggregate, a granite aggregate, right? So if these failure mechanisms are different, do we need to start changing our design procedures? Okay. And lastly, the mechanical performance here, again, since the failure mode is different, measuring strength and modulus is not giving you the whole picture. Okay. Uh, if we had more time, I'd talk a little bit about the slab capacity study we did, because we showed that even though concrete with wrap had a lower strength and a lower modulus, its slab capacity was actually increased relative to the control. Okay, so higher modulus was able to sort of withstand greater strains. It also has a greater fracture energy. Okay, so that asphalt film can actually absorb a lot of fracture uh, by basically kind of sucking in those cracks and having the cracks propagate around the asphalt. It can absorb a lot of energy. All right, so the fracture properties can be improved by using wrap. Okay, so again, if our slab capacity is improved, right, that tells us that, okay, we don't necessarily have to change our pavement thickness design. But if you go to a conventional design methodology based on strength, right, it tells you that you have to build a thicker pavement section. So again, this is just the closing picture is, if we use these recycled materials, we have to think about them differently. We might have to start characterizing our concrete performance based on different metrics. All right, and that's kind of all I really wanted to cover. So, yeah, do we have any questions?
Thank you so much, Alex.
Yeah.
Yeah, I'll open the floor for a question. Does anyone have any question?
I have a question.
Mhm.
Yep.
So I'm working on roller compacted concrete, and mainly my research is in the early fresh properties within the first hours. What is the time scale at which aggregates will draw water from that free available water? I'm using dolomitic limestone with 3.8% absorption, which is pretty high. Do you have a time frame or literature on?
Yeah, there have been a handful of studies. So as I recall from what I've seen, is typically things like limestone, something with a not too high of an absorption capacity, is usually a handful of hours, maybe up to 12 hours or something. And again, things like RCA is probably going to take 24 to 48 hours, if not longer. Uh, so I have some of those references. I'd have to look back in some of my papers. They're probably in my RCA ITZ paper, if you wanted to look at that one. But it's something you can measure. It's something you can quantify and figure out. And maybe that's what you have to do. It probably also has a lot to do with the size of the pores and the distribution of those pores. Right. So the larger pores are probably will be able to absorb that moisture much faster than a much more probably not nanoscopic, but probably more micro scale, I guess, pores will probably take longer to absorb that moisture.
Okay, and when you design, for example, a specific water cement ratio, usually standard concrete is going to provide proportions at SSD. Would you rather recommend having stock moisture content design parameters, so excluding the water that's going to be absorbed or given by the aggregates?
So are you So you're saying you're mixing your concrete at SSD? Of course, our mix design is assuming SSD.
Yeah, but let's say
right?
you have aggregate on the drier side.
Yeah.
Would you still batch to have that stock moisture condition water cement ratio?
Yeah, I would say you still should batch your water appropriately, assuming you have let's say we'll call it a normal moisture absorption capacity, right? I mean, if we're looking at a granite that has 0.5% moisture absorption, it's probably not going to make a whole lot of difference if you adjust the water there or not, right? But when you're getting into these ones that want to absorb a lot of moisture, that's when you're running into issues. So in the case of roller compacted, are you mixing everything in dry?
Yeah, well, in the lab, I'm using some aggregates that are close to be dry, some other half of SSD. And since I'm measuring properties in the first 30 minutes after batching, I'm usually excluding that absorption.
Yeah.
So I don't over design in water to account for that water absorption.
Yeah, well, RCC is kind of a different animal, so I'd probably agree with your methodology there. It would be interesting. Well, you can't exactly measure a slump, so are you somehow measuring workability
Yeah,
or some sort of flowability?
compactability with the gyratory.
Okay. It would be interesting to see. Are you looking at that as a function of time?
Yeah.
So is it decreasing fast? Whatever metric you're looking at, is it seem to be more affected by, let's say, purely oven dry versus partially saturated?
I haven't tried that, but
Okay.
I think that's a good avenue considering your talk.
Yeah, I mean, especially so we've done those studies with RCA, and we were able to track pretty much slump loss in conventional concrete, right? And since oven dry RCA wants to absorb a lot of that moisture, your slump loss just plummets, right? You run out of workability fast. And then yeah, with something like partially saturated, it's workable for a few hours,
Yeah.
right? So I would not be surprised if you see something similar even at these early ages with RCC. And it would be interesting to extend your study, right? Just do a few experiments just to see what happens if you do use RCA um, in an oven dry condition versus something partially saturated. A number of years ago, one of Raessler's 506 class projects was RCC with RCA. And I forget which group did that. This was probably back in 2013, 2014. And I don't think that the data ever went anywhere because, again, we saw a lot of variability and a lot of problems. So, and I don't know if did Jeff Plahusik look at RCA? I don't think so.
I think in Sachendra too.
Yeah,
Fiber.
I think it is more with fiber. That's
Okay.
what we looked into.
Okay.
Okay. Thank you for your explanation.
Yeah. If I can help at all, let me know.
Thank you.
Is there any more question?
Can I ask Alex?
Yeah.
Maybe I'll end up all of our sessions and maybe we can talk after that. How about that, Kwang?
Talk. Oh, okay.
Yeah, for the people in the class. Yep. So yeah, thank you, Alex, for the nice presentation. We really appreciate your time.
Yeah, thanks for inviting.
Yeah, we have. Thank you so much for accepting our invitation and coming and speaking. So yeah, I think that's it for the presentation. If anybody wants to go or something, that's all for the thing. Thank you so much for coming, and people here in person as well. We would like to thank you all for coming here. Thank you so much. Yeah, Kwang, go ahead and ask the question.
Oh, Alex, just a general question. Do you think that RCA and then your work, can it be benefit in the 3D printing?
For 3D printing of let's say concrete or some sort of mortar?
If you use the RCA, can it use in the 3D printing, concrete printing?
Right, but are you saying RCA is an aggregate in a 3D printed concrete or as something else?
That's something else. It's, I don't know. Right now, I know that 3D printings for the for concrete printing is they don't use aggregate, right? They use fine aggregate or
Yeah, you typically either
not the
yeah, a lot of people are printing paste. Some are doing
paste
like a
and mortar.
grout with a fine or yeah, mortar.
Yeah, but do you think that any work that they use RCA for the 3D printing?
I'll say not that I've heard of, but that doesn't mean that someone hasn't tried it. Probably one of the benefits is if the so the fine RCA is fairly angular and kind of has the will kind of act as a viscosity modifier if you want to think about it that way, right? You'll kind of have some slump loss just because of the particle shapes and sizes. So forgetting even the moisture content, right? It does affect your workability quite a bit. So if you use it to kind of modify the viscosity, I could see how that could be a benefit. The bigger issue I've seen in all of these studies and in talking to people is precise control of the rheology, right? So you really want to have a very fine, tight control over basically your viscosity, right? So as the cement's hydrating, that's being adjusted. So you have people who are trying to do inline mixing of chemical admixtures and people who are trying to mix it and print it immediately, and other groups have paste that's been sitting around for 30 minutes and they're trying to print it and it's not working. So if we're having that many problems with just a plain cement paste mix, and we have enough issues with RCA kind of absorbing moisture and things, RCA might be just more problem than it's worth, at least at this stage in the research for any of that, I would say.
So you think that, but you think that ITZ problem gonna be it's gonna be problematic in the 3D printing? I don't see that because the 3D printing ITZ most of like both focus on the zone that between the aggregate and the surrounding, right? But if we don't have aggregate, then the ITZ problem is solved.
Yeah, you have no ITZ in cement paste, right? That's why it's one of the reasons why mortar will be lower strength than a cement paste at the same water cement ratio, right?
Yeah.
So yeah, I mean, even if you use a fine enough aggregate that's on the size scale of the cement particles, right, then there's no wall effect. There can't be an ITZ. But I think with 3D printing, they have shown that there is like a layer ITZ, right? Layer to layer sort of.
I think right now they do printing layer by layer. But I have one of my friend in Australia. He doing the topology for the 3D concrete printing.
Okay.
So it could be if imagine they doing this a small scale, but to learn about that how the 3D printings affect the topology of the structures, right? But imagine if we enlarge the scale of the structures, we enlarge by using a bigger nozzle or something, then we can put the aggregate in there in order to build a large scale structures. Now the problems here is that if I use the RCA recycled concrete, does it benefit the 3D structure or not? I don't know. It's going to be the future, but I'm just curious.
Yeah. Yeah, I would caution avoiding recycled aggregates for, probably 10, 20 years before we even consider putting that in 3D printed materials, right? There's enough issues we have to solve now, and just adding another layer of complexity with recycled aggregates behaving differently. Yeah, I don't know that that's a
Mhm.
it's a solution for sustainability. I can see how people are going to see it as a very
Yeah,
important
yeah.
step. But from what I've seen from presentations and things, we just don't have enough figured out yet of 3D printing, even
Yeah.
paste or mortar, to even scale it to concrete. I mean, I've only even seen a handful of concrete 3D printing, right? As you said, it's mostly mortar or paste.
Maybe we still
Yeah,
far from it.
yeah,
Thanks, Alec.
yeah.
Thanks for answering.
Yep, I think that's all. If anyone else has anything.
Let's see who's. Where did I lose my?
Not sure if the other person has any questions. So thank you so much, Alex.
Yeah, yeah.
Thanks a
Again,
lot,
thanks.
Alex.
Yeah,
Nice to
thanks
see
for the
you.
invite. Yeah, it was good seeing you.
Yeah,
So, so Kwang, you're now at Beckman. Is that what I heard?
Yeah,
yeah.
I'm in
Okay.
Beckman.
And then, so you're doing a postdoc there, or what sort of position do you have?
Postdoc, yeah, I'm doing
Okay.
postdoc there.
And what's the plan?
The plans next
Yeah,
year's like so I'm still planning for the faculty in civil,
okay.
but what I'm trying to do is implement an uh, basically NDE for here they have very interesting lab. I mean they do what they call a quantitative method for let's say they use ultrasound in order to quantify the property of something that we can't see. For example, it's the liver cell. It's impossible in order for us to see something in the bare eye. But we're using the SEM already. That's traditional. But why don't we use ultrasound? Because it's cheaper, it's safer, and then it's portable.
Mm-hmm.
So that's why they create the lab. Ultrasound is just like one technique in order to find the concept applying that you can quantify the property of the material.
Mm-hmm.
It is. So so I learned the technique that I can quantify the material properties, the structure of the small scale materials, right? Then I can apply in anywhere, basically, like maybe in the concrete or whatever, it's small scale. So I want to create a lab, something like that. I use let's call it the quantitative method lab for civil,
Okay.
where I use the ultrasound in order to characterize the material properties and find the quantify the structures.
Okay.
That's the plan.
That sounds pretty
So
cool.
yeah, I can imagine before I joined this lab, but after I joined, I learned a lot about how can I quantify and then characterize the property of the material. It is. I think it can open a new door in material in concrete, because that people use the SEM because we can see, we can quantify.
Yeah.
But imagine that if you go to the construction site, you cannot cut or do something with the structure, right? You can slide it. So you have
Yeah.
to use some invasive technique to estimate about to characterize the property of the existing structures.
Mm-hmm.
And then here I come, and so that's what I plan to apply for the faculties in that way.
Okay.
That I don't know if like do you know about a market next year or this year?
I haven't heard anything about next year. I mean, there's only a handful of positions I've heard of this year.
This year, you mean that?
Yeah, the most recent call, you would have had to have applied like December probably for anything for the following year. And I think coronavirus has slowed that down. So there might be sort of a dip in available positions in the coming year. I don't know. I mean, universities plan these faculty positions years in advance, right? So if someone wants to hire someone, right, you're looking at like a 5-year outlook, right? Because then you have to talk to the dean. Dean has to allocate the money. So there may or may not be a dip in available positions in the near future. Again, because a lot of these positions are kind of planned. So I don't know what to say. I have not heard of anything yet, right? But you can expect most calls to start probably late summer, and then they usually have deadlines for application anywhere from October through probably February. But in your position, since you're kind of looking at a few different fields, you should broaden your scope to even looking at like mechanical engineering, or aerospace will often have
mechanical.
Mechanical or even aerospace for NDE. So you may be able to find other positions. Yeah. So never limit yourself to just one application, right? Be sure to just look at all calls.
I think I just dropped. Sorry.
You had froze for a moment.
Yeah, but very nice to see you, Alex. And,
yeah. Good catching up.